you've been given an introduction to flux growth and various growth techniques, and since I'm talking in the middle, JP sort of suggested I focus on a slightly different variant. What I want to do today is what I hope, give you what I hope will be one of the most important talks of your career, which is how to come up with ideas, okay, in the context of having the freedom to grow things. Okay, so it's going to be a storytelling exercise. I'll use different materials, different physics as examples, but more importantly, I just want you to get a flavor of how you can come up with ideas. Okay, and as JP said, interrupt, make fun of, whatever. Probably about 15 slides in, you'll realize I truly have no shame and very few inhibitions. So we can keep going with that. My former student is sitting there wondering what the hell I'm going to do. You'll find out soon. Okay? All right, so with that done, let me start with conclusions, okay? Design, discovery, growth of novel materials is the heart and soul of what I would call new materials physics, okay? Synthesis combined with broad characterization tools and sort of an eclectic and perhaps even eccentric interest in novel states really is the wellspring from which I think humanity is going to solve its problems. Humanity has painted itself into a corner. We have limited energy, limited resources, limited many things. If we don't solve this by discovering new materials, we'll solve it by killing off 50 or 90% of the population. I'd prefer to discover new materials. Okay, so, but I mean, those are sort of the two options. It's the horse riders of the apocalypse or us. Okay, choose. All right, and our challenge is to refine and unify and utilize this powerful tool as efficiently as possible and teach it to as many people as possible, and that's sort of why I'm here. So, for luck or for the iron, we can start with horseshoes. Okay, and the reason I want to start with horseshoes is because there's the horseshoe theory of politics, which probably many of you are familiar with. And the horseshoe theory of politics is it's not a linear sort of progression of far right, middle, and far left. They actually bend around. And when you look at sort of the far left and far right, they are more like each other than they actually want to admit. So you can insert whichever examples you want here, and I'm sure you have many, and that would derail us, and DOE doesn't allow me to talk about this anymore. So on the other hand, I maintain we can have a horseshoe theory of physics because you have sort of experimental research, theoretical research, but exploratory synthesis and really sort of closed form Einstein type theory, they're closer than you may think. Okay? Because at least with theory, I've had theorists say, oh, it's just trivial. You just change a prefactor and whatever to go from an electron phonon superconductor to inside a neutron star to the quark gluon plasma. It's trivial. For them. On the other hand, what is really trivial is you can take a structure, take the half-Heusler structure, which is rock salt plus 1, okay, and we can decorate it with different elements, okay. I can go ti nickel tin, manganese nickel antimony, blah blah blah. I can go from a 1 eV semiconductor to a 700 Kelvin ferromagnet to the heaviest heavy fermion, non-centrosymmetric superconductor, and post-topological insulator. That is trivial, and that's neat. Okay? So, the nice thing, the advantage of synthesis over theory is instead of just dreaming about things could be, we get to have reality. We get to have our manipulations and ideas become physical reality. If you're wondering what these paintings are, please look at the myth of Pygmalion, okay? Right? Whatever. Good. So, how do we do this? What we try to do is project a Hamiltonian onto the periodic table and then grow substances. Now, that's sort of a grandiose statement, but let me give you an idea of what I mean by that. Okay? So, for superconductivity, project a Hamiltonian. Well, if we look at parts of the periodic table, I have light elements, which can mean tight binding, high phonon frequencies. Transition metals might give me a large density of states. They also give me the possibility of tuning band filling, possible fragile magnetism. I'll get to that later. I can tune band filling by substituting an alkali or alkali earth for devoutly valences of other types. I can tune bandwidth by going up and down a column. I can tune my local moments or have heavy fermions or fragile moments. This is what I mean by projecting a Hamiltonian. These are all terms that you can imagine being in a Hamiltonian. Okay? But the number of potential compounds is huge. Okay? If I just get rid of the radioactive and the noble elements, I still have 80 elements to play with. And if I do some really cheesy combinatorials, I can make estimates of how many binary and ternary compounds, and then you have quaternary and higher. You have millions upon millions of possible compounds that might exist, might be known, or might be discovered. So really the question is, how do you try to figure out, what do you look at? The phase space is too big for blind combinatorials, so how do we choose what sample to make? Okay? So, what I want to do in this talk is give you an idea, okay, of how to choose a sample, of how to coax the unicorn out of the forest. Okay? Classical paintings again, good stuff. Okay. How to encourage visions of sugar plums to dance in your head. Okay? For those of you familiar with English language poetry, or if we don't want sugar plums, maybe other things dancing in your head. Okay? Yeah, that's how I go to sleep. And what I really want to do is give you an idea how to create the idea for new materials and then have it manifest itself. Okay? So in that sense, I consider this to be an incredibly important talk. Right? So, in my own group, there are three basic motivations for making a growth. There's sort of three ways we go about exploring phase space. Okay? Sometimes you want a specific compound. Sometimes you want a specific ground state. And sometimes you want to search for known and unknown unknowns. Okay? And I will go over each of these. Okay? The first one is obvious. The other ones become a little more subtle. Okay? Now, these are clearly overlapping and they often flow into each other, and I'll try to give you a flavor of that as well. Now, ideally, what I wanted to do was have this left up there because I'm going to start with a specific one. There's not space in this room for this, so JP, I'll have to do this with apologies. JP's giving you his own swag. One of my students decided this was important enough to have on our group t-shirt. So you see, t-shirts actually do matter. So, okay, so for the rest of the talk, we can refer to this. Oh yeah, when I did this in Madrid, they applauded, right? Yeah. And one of my students, you have it on tape, dude. Here, you can get the back.
Give me that again.
Right. It was supposed to be may your crystals, but Nahian was a little vague on the language, so it might have a double meaning. All right, so we can keep track of what we're doing. All right? Okay, so let's start with wanting a specific compound, okay? This greatly reduces phase space. All possibilities become basically want a specific compound projected on the periodic table as a delta function. Okay? Yeah. That's about the most sophisticated mathematics I'm going to give you. All right? Now, it's a specific compound, but it's often a specific compound that's the birth of a new field, at least if you're choosing your specific compound correctly. So let me give you some examples of how we've gone about doing this, how we've used growth to get there, and then also to motivate going into the next steps. Okay? So, it's worth noting that in each of these cases, and we'll go through them, the strong desire to have a specific compound so that we could get to the measurements, because we're physicists after all, led us to extend our growth techniques and capabilities, and that feeds back into the milieu. Okay? So, first example, borocarbides. In 1994, there were two related superconducting compounds, yttrium-palladium borocarbide, lutetium-nickel borocarbide, with TCs that were really quite respectable at the time, modulo 20 Kelvin. Okay? We really wanted to grow lutetium-nickel borocarbide. Okay? Now, this is tricky. It's a quaternary compound, it's a refractory compound, and it's incongruently melting. The only thing we're missing is toxic or radioactive, but I mean, it is an unpleasant material to try to make. On the other hand, after playing around for a while, we realized that if you look at the nickel-boron binary phase diagram, and Helena hopefully went over binary phase diagrams with you nicely, you see that there's this beautiful cascade of eutectics, and you have some eutectics going down to near 1,000, but you can also see that below 1,500, you'll have a lot of exposed liquid to play with. So we came up with a two-step process where we could grow this from 1,500 down to about 1,200, then cool to room temperature, reseal, and then heat up to 1,200 to decant, and you can get lovely single crystals that opened up the physics of these materials. Now, lutetium-nickel borocarbon, which is what we originally wanted, has a TC around 17. It has a relatively isotropic, but also disappointingly low Hc2. It was sort of cute. But on the other hand, having mastered the growth of the lutetium nickel boron carbide, it opens up the possibility to look at all the other rare earths, and you can form this material for non-magnetic lutetium or yttrium, but also magnetic thulium, erbium, holmium, dysprosium, and you can look at the interactions of local moment magnetism and superconductivity. Okay? And that was a wonderful way to play around with these materials. So, we initially wanted a specific compound, lutetium nickel boron carbide. Then we wanted to explore specific ground state, superconductivity and magnetism in these materials. But then often when you play with new materials, you can run into surprises, either intentionally or accidentally. In this case, the surprise was these materials manifest some of the clearest examples of hexagonal to square vortex lattice transitions. Okay? And we could play around with those. So the point I want to make is you often have a sort of evolution from one of these motivations to another. Let's look at another example. In '97, we were interested in growing rare earth mag zinc quasicrystals. Okay? Basically, we wanted to study their magnetic properties, but as a first step, we needed to make single phase, single grain, because all prior samples had been polygrain and polyphase, and that led to difficulties. Okay? So, here's the phase diagram we ultimately were able to establish. Basically, we have a quasicrystalline phase that we can grow out of excess magnesium and zinc. Okay? Now, in order to handle this, okay, we needed to sort of devise a way of working with very reactive magnesium-rich solutions. Okay? So instead of using alumina, we had to shift to tantalum, and since we like to decant, we came up with something we called a 3-cap crucible. Okay? So a tantalum tube, we can make these caps nicely, weld them in the bottom, drill holes in the middle one, clamp it in, and then weld this in, and then seal this in silica. And this allows us to grow and decant, as you've gone over with the flux growth already, okay, in a tantalum vessel. Okay? Now, with that in hand, we were able to grow what is, ended up being the iconic pictures of quasicrystals. You can count, Lauren, you can count with me, 1, 2, 3, 4, 5. These are 5-sided facets. This is a forbidden, historically crystallographic symmetry. Okay? So A, it was pretty and nice, but B, what it allowed us to do then is to look at materials that had highly ordered but not periodic rare earth sublattices. Okay? We could grow it for the non-magnetic yttrium, but we could also grow it for the non-CEF split gadolinium and the CEF split terbium through erbium. Okay? We were able to find that these were ideal spin glasses. There was no long-range magnetic ordering, but they ordered in just canonical spin glass form. And with that under control, if we think we have something canonical, we can ask it questions. Okay? If it's a model system, prove it. Use it to ask something profound. Okay? So we could ask, is there a difference between a Heisenberg and a non-Heisenberg spin glass? Okay? So we can have our paramagnetic theta versus de Gennes factor for the pure materials, for a non-magnetic yttrium and CF split terbium, non-magnetic yttrium and non-CF split gadolinium. All of the thetas scale with de Gennes factor, which is what you'd anticipate. On the other hand, if we look at the freezing temperature versus theta, it splits into 2 manifolds. Okay? Now, you can understand this simply by thinking of marbles. If the floor is covered with spherical marbles, it's slippery. On the other hand, if you square up these marbles, make them less spherical, okay, it becomes less slippery. If we have a spin glass, if it's a Heisenberg, a spherical symmetry, it will freeze at a lower temperature than the non-Heisenberg. Okay? So, what we can see here then again is a progression from we want a specific compound, we want to see can we grow single phase yttrium mag zinc quasicrystal, to wanting to study a specific ground state spin glasses, to then trying to ask questions about what we have, what are the effects of CF splitting on the spin glass state. Okay. A few more want a specific compounds as we warm up to the other motivations. Okay. In early 2001, there were rumors that MGB2 might superconduct near 40 Kelvin. In the questions, if you want me to elaborate on what the hell do I mean by rumors, I'm happy to tell stories. Other people here can elaborate and help with them. Okay? Now, that means we really, really wanted to grow MGB2. So quick, look at the binary phase diagram. Here's magnesium, here's boron. Find the liquidus line, we're good. there is no liquidus line. Okay? This is a highly inauspicious phase diagram for solution growth. And despite many attempts to grow this out of binaries, ternaries, quaternaries, I used almost a kilo of platinum trying to grow this. Now, I gave it back. Okay? We recycle our platinum. You don't need to dig through my trash. But it was not something we could grow as single crystals, okay, at ambient pressure, okay? Because there is no liquidus. On the other hand, with the tantalum tubes, with stuff that we had on hand, we rapidly realized that we could grow incredibly high purity MGB2 polycrystalline materials by just having high purity boron and high purity magnesium in a tantalum can, and at 950 you have a 1/3 atmosphere partial pressure magnesium, and it sucks the magnesium out of the air. So you can get it by diffusion. Okay? And the key was having high purity boron. If you have low purity boron, then you have low purity MGB2 and you have sort of crap results. Okay? Now, what that meant is, since we had isotopic boron on hand, we could immediately make isotopically pure MGB2 and see a 1 Kelvin isotope shift in magnetization and resistivity and specific heat. And this immediately made this clear to us and the community that this was a phonon-mediated superconductor. Okay? We could also, of course, characterize the basic properties. It's a fantastic metal. It has a moderately high Hc2, and we could even infer a relatively large anisotropy in the pure compound. And MGB2 for us, and for all of you too, should be a lesson, which is sometimes you can do a lot with polycrystalline samples. Look, our arrogance, our happiness is we do single crystals, but we're also physicists and we'll measure the sample we can get our hands on. So with polycrystalline MGB2, we enjoyed a month where we basically had a PRL a week. And it was fun. It was like surfing a tsunami with MGB2. But, it was really neat. Okay? So, sometimes you want a specific compound, but then, of course, we wanted to start studying the ground state. Okay? What can we learn about superconductivity in this material? And we can put it in context. Here's niobium-3 tin. This is a highly optimized superconductor. There have been decades, and David Larblastier and co-workers have grunted and sweated to get the last iotas out of the Hc2 here so it could be a good practical magnet material, okay? Now, pure MGB2, it has a higher TC, but the Hc2 is a little disappointing. On the other hand, since you have graphitic layers of boron, it's not too much of a revelation that maybe you want to substitute in some carbon into these graphitic layers, and as you do so, you mildly suppress TC from 40 to about 35, but Hc2 marches up. So in bulk, carbon-doped MGB2, you can supersede the Hc2 of niobium-3 tin over the whole temperature range. And at this point, humanity, not my own group, but humanity as a whole, has taken MGB2 and has turned it into a practical superconductor. You now have what's called the MGB2 zone of use, because here, niobium-3 tin doesn't even superconduct, and MGB2 is superconducting and has a relatively respectable Hc2. You can make nice powders, you can do powder and tube multi-filament, you can wind them in coils, and you have prototypical Helmholtz geometry MRIs that you can cool at 20 Kelvin that are lighter and cheaper to use. Okay? So MGB2 is actually finding a niche in industry, about 15 years after. Oh my God, what's that in terms of a discovery? Now, we're getting close to talking about other things. So, 2008, we really, really wanted to grow potassium substituted barium iron to arsenic 2. Okay? So, within 14 hours of reading that this could superconduct in polycrystalline form, we had grown sizable crystals and were studying its properties. It was obvious you could grow this out of tin. Okay? It's obvious if you add nutmeg to a white sauce, it'll taste better. No, if it's not obvious to you, you don't cook enough. If it's not obvious that you don't grow it out of tin, you haven't done flux growth enough. But if you've done it enough, it's obvious. Okay? Materials work is a lot like cooking. Okay? And I mean that in the highest praise, in the sense that it is based on experience, intuition, and creativity. Okay? So, with single crystals, we can start measuring anisotropic properties. Okay? So here's the Hc2. This has a TC a little below 30, and by 14 Tesla, we're barely suppressing TC. So it was immediately clear that we were going to have a huge Hc2, and also if we look at this, the anisotropy is not very large. Now, This required going to the National High Magnetic Field Laboratory, where we could go to higher fields. Okay? We can see that Hc2 is indeed really large. The anisotropy is getting smaller as we go to higher fields. And if you remember, 20 Kelvin was sort of exciting for MGB2. Well, 20 Kelvin here, the lower Hc2 is in excess of 40 Tesla. Okay? What this meant is, in 2008, when we made these measurements, immediately the iron arsenides were not only amazing, interesting physics, but they also had possibility of being the next practical superconductor if you can make wires, if you can get the critical current under control, and those are both big, huge, hairy ifs. It's been almost 30, 40 years of high TCs, and we're still struggling with those ifs. Okay. Now, let me use the arsenides as a way of really more closely examining how one specific compound feeds into these, and then we'll start with these as their own individual motivations. Okay? So, the iron arsenides are a great example. Yep, sorry, I got ahead of myself. So, starting with barium iron to arsenic 2, we really wanted to determine the range and rules for superconductivity. So, we can go back to our periodic table and say, look, due to some beautiful work by a former postdoc of ours, Athena Sefasafat, she found that you could actually turn on superconductivity by substituting cobalt in some of these materials. We then wanted to see to what extent can you chase this out, first in the 3Ds, and then down to the 4Ds and the 5Ds. Okay? With that, we now, instead of having millions of compounds, are talking about a dozen substituted series. Okay? And what we could do is we could establish the rules for superconductivity. We could now make physicists' phase diagrams, not material scientists' phase diagrams of temperature and composition, but temperature and, well, composition is the same type of thing, it's just different temperatures. We're talking about transition temperatures, magnetic structural and superconductivity. As we substitute in cobalt, rhodium, nickel, palladium, we can see for isoelectronic substitution we have virtually the same phase diagram. If we shift over one, the phase diagram is scaled by a factor of 2. The TC dome scales the number of extra electrons, and we could come up with what is really sort of the iconic phase diagram or map for how the structural and magnetic phases interact with each other. Okay? Now, that's wanting to study a specific state, superconductivity. Sometime you want to look at unknowns, okay? And this is going to be something we'll refer to as a known unknown later on. But here's a simple question. It's what I call sort of a clever monkey question, okay? Barium, strontium, well, what about calcium and magnesium? And the reason I say this is barium and strontium iron to arsenic 2 were known compounds before the first crystals were grown. These were materials that were in the structural literature, they were known, and basically the realization was you can actually dope these and get these to superconduct. But they were known materials. On the other hand, calcium iron to arsenic 2 was not a known compound. But at this point, obviously, we'd like to see, and this is a rare example of actually growing a new material first in single crystal form, in large form. So we could grow this nicely out of tin. You can also grow it out of iron arsenic. You can get beautiful crystals. It has a sharp, strongly coupled first order structural and magnetic phase transition, and it actually has become the extreme member of this 1-2 series, and more importantly, and at the end of this talk I hope to get to, the springing off point for looking at other related series. Now, you could make calcium. On the other hand, magnesium seems to not work. It doesn't work as a line compound. It doesn't even work for substitution. We tried a lot. I know Bob Kava tried a lot. I don't know if JP tried at some point or not, but it just doesn't seem to go. And sometimes when you explore for unknowns, nature says, not going to work. All right. Now, let's get to sort of the first step of the less usual part of the talk. Okay? Let's start with wanting a specific ground state and see how this narrows phase space. Okay? Because now, this is what I sort of refer to as negotiating with nature. Okay? You have an idea, and now let's negotiate with nature and see if you can make that idea manifest. Okay? So, I'll give two examples of this, one old and one new. This is the old one. Let's say you want a praseodymium heavy fermion. Okay? Let's see how you go about that. That's a very simple idea. Okay? Now, if you want this, okay, you're going to need to preserve entropy to low enough temperatures so you can have some sort of hybridization and transfer of this entropy from the 4F to the conduction electrons. Okay? So, The problem is praseodymium is a non-Kramer's ion, which means it can have a singlet ground state. So the first problem here is you need to preserve your entropy. Okay? So we can look at Lely-Wolff diagrams. These are looking at the CF splittings in rare earths in cubic point symmetry. And the main point to note is the gamma-3 is a non-magnetic doublet, okay? Which means if you could preserve the gamma-3 state to low enough temperatures, then you may have some entropy to have things happen. Okay? Now, back in the day when I was looking at this, Pearsons was still in book form. Okay? So what you would do is you would spread Pearsons crystallography out. Those were the good old days. You would have phase diagrams and Pearsons spread out over various desks. And it was a good way to spend a Friday afternoon just fantasizing. You know, visions of sugar plums dance in your head. Okay? No, it really is. It's neat. My former postdoc, Ian Fisher, would say he and his brother would steal cookies, hide under the couch, and plot the overthrow of the parental authority. Okay, but I mean, it's a sort of the same fantasy. It's just sort of a nice, warm, wow, I wonder if I could do that. Okay? So, how do we use these? Well, we want a cubic unit cell because we want a cubic point symmetry for a single rare earth site. So, cubic unit cell, single rare earth site, rare earth and cubic point symmetry, rare earth equal praseodymium. This is a cascade that starts narrowing what you look at. Okay? So, if we look at Pearsons, here's one of the many pages out of Pearsons. Here's CF16, otherwise known as Heusler. Okay? And if we look at it, underneath all of this here, you have silver 2 indium praseodymium. Okay? Cubic point symmetry, praseodymium. Okay, now we can check literature. And there actually aren't that many that fit this cascade. This one, when we check literature, Rosemarie Galera from Grenoble had looked at this a decade or so earlier when they were interested in singlet ground state praseodymium, and this was not a singlet ground state, so it was a 2-page conference proceedings. Thank God for 2-page conference proceedings. Okay, and then they moved on. We were able to reproduce their CF splitting, okay, both from inelastic neutron scattering, gamma-3 separated by 6 MeV, so about 60 Kelvin from the highest state. Okay, we can measure specific heat, fit it to this distribution of Schottky's, but at low temperature something's happening, and if we look at low temperature, we have a linear specific heat going through 0, 0, plot at C over T, you have over 6 joules per mole K squared. Okay? So, can entropy be preserved in Prasio systems to low enough temperatures to allow for hybridization? Yes, if you do it carefully. Okay? Can a Prasio-based sample go heavy? Yes, but it's fundamentally different. This is a non-magnetic doublet. So if you want to think of a heavy fermion being a local moment dynamically screened by conduction electrons, that's not the case here. This is probably, using old vocabulary, a Jahn-Teller transition trying to be dynamically screened, or you can, in modern language, say a quadrupolar or something like that. It's all doing with the CEF levels of the specific species. But the key is this idea, praseodymium heavy fermions, this material really opened the area of this type of research, and it's still an area that's going on. Okay? Now that's one example of using an idea to limit phase space. Let's look at a second example of wanting a specific ground state, and this is a more contemporary one. Fragile magnets, what I call fragile magnets. Okay? So, this now is going to incorporate computational and computer programs at a certain level. Okay? So, let's see how this works. I want more high-T superconductors. Now, that is not a novel statement. Okay? A lot of people have had that idea. I think Sung had that idea a few days after Bednorz and Mueller came out with the cuprates, as did many other people. Okay? Now, the problem is this is not a sharp desire. This is a vague aching. Okay? Let's try to let's try to sharpen it. Okay? So let's look at some of the high TCs we know and love. We have copper-based, we have iron-based, and in each of these cases, what we can see is we have our superconductivity in proximity or right where an antiferromagnetic transition crashes. Okay? So, in each case, we're proximal to some sort of fragile magnetic state. So let me sharpen my desire. Let's rephrase. I want to find transition metal-based fragile magnets. That's a somewhat sharper desire. Okay? Now, there's an implicit, and maybe then I can find high TCs. But at least I have an operational step that's getting me a little closer. Now, let's start with Okay. How many of you have watched Casablanca? Oh God, so few. All right, the rest of you watch it, okay? This is when we round up the usual suspects, Frenchie, okay? So if I want fragile transition magnetism, these are the usual suspects: chromium, iron, cobalt, nickel. If your favorite transition metal is missing, fine, we could look at all of these, but God, this is enough to start with, okay? And the reason I say that's enough to start with, even with these four, we have a substantial phase space. And let me give you a sense of that. Let's look at just cobalt, okay? Now, instead of these, I've got computerized Pearsons, okay? This is, oh boy, the things you can do with computerized Pearsons. So I can do cuts. I can say, hey, Pearsons, I want cobalt-bearing compound, tetragonal, unit cell ternary. Okay? I'm taking a subset of a subset of a subset. Okay? And Pearson says, yeah, you only got about 1,100 compounds to look at. Now, Pearson's is a little stupid because many of these are alloys, many of these are repetition, but even you get rid of that, you've got, several hundred, and that's just tetragonal. Heaven forbid you go to hexagonal, this, that, and the other. Okay? Now, okay, we want to come up with ways of trying to make this a little easier. How do we try to sort through this? Okay? Well, now we turn to our colleagues who do band structure, okay? And we try to be kind to them. Because as an experimentalist, I can dope things, I can make alloys, I can do all sorts of things. But the computational people find that difficult because if you want to do it honestly, you have to do either supercells or you have to handle the disorder or all sorts of hideous stuff. So fine. Let's try to, instead of looking at doping, we can look at pressure. Okay? So computational efforts. We want to find something that indicates a degree of fragility, okay? So computation of pressure effects on pure compounds is going to be easier for computation, okay? Now, if you want to be back to the Hamiltonian, what you could say is this is emphasizing bandwidth a little more than band filling, okay, to first order. But you know what? With a lot of these superconductors, the effects of pressure and the effects of doping are really quite similar. You suppress your structural magnetic, you get superconductivity. You suppress your structural magnetic, you get superconductivity. This is not surprising. If you're saying something's on a high slope in one dimension, it often can be a high slope in the other dimension. I mean, there could be a saddle point in the other dimension, but that's not always the case. Okay, so this is good enough. So, what do? Experimentally, we're trying to identify promising candidates through intuition, through looking at various structures, through looking at literature. We try to make them, and then we can measure magnetization and transport up to 1, 2, 8 or more GPa in our lab. We can go higher in other places. We can use chemical substitution to try to push further or do things simply. And systems that do show fragility, we're starting to chase and see how they go down. Computationally, we're trying to provide benchmarks to the computational groups we're working with. There are 3 throughout the world at this point that we're playing with to try to develop methodologies to identify fragility, okay? Well, once the methodologies are considered reliable, and we're still sort of struggling on that, we're trying to use them to identify first candidate materials, and then we try to feed the information back into the computational work. This is actually much harder than you think, especially when you start keeping in mind that we want antiferromagnets, and there's a whole ambiguity of what's the ordering wave vector. Okay, so you need to do chi-q calculations as well. So we're starting to do this. We're continuing to do this. It's not easy, but we're still narrowing phase space. Okay? All right. Third motivation. This is one that I really want to spend some time on because it's the fun one. It's the beautiful one. Okay? So, unknowns. There are known unknowns. I give them 2 names, run across the series, study a family. I'll explain what I mean. These are ones we've sort of touched on, okay? Run across the series, basically, if you have a material that forms in a rare earth XY, then you probably have other rare earth XYs nearby, okay? So, often what's neat to do is to take rare earth series and see how their magnetic and electronic properties vary across the rare earths. Tomorrow I'll give a colloquium in Georgetown on how the physicist uses the rare earth series as a tool. Okay? That's a whole separate colloquium. Okay? What you can do is you can form rare earth bismuth platinum. This I did as a postdoc, and people are now returning to it for a whole bunch of different things. Okay? Diantimonides, 1,2,2s, silver antimonides. The list is actually 2 or 3 times the size. These explorations lead to basically the knowledge of what is the magnetic anisotropy, what are the electronic states that a series offers, and gives some hints of how you can tune it. We have discovered wonderful new phases by doing this, but perhaps more importantly, we've laid out the landscape of potential model systems for other people in future decades as they want to look at specific types of magnetism, electronics, etc. Now, another exploration of an unknown is of a given structure class. And this is what I touched upon already when we said, look, we have barium iron 2 arsenic 2, strontium iron 2 arsenic 2. I wonder if calcium forms. Yes. I wonder if magnesium forms. No. Okay? This is studying, again, a known unknown. Okay? I know these form, and maybe these form also. Okay? Now, that's sort of the first step. Okay? But let's talk about the more interesting one. Searches for unknown unknowns. And by the way, for anyone who thinks that I'm just copying off of Donald Rumsfeld, you don't know the history of this quote. It was a quote that was used in NASA a lot in the old days. It's basically known in engineering and in a lot of other sciences of trying to predict or understand where surprises might come from. Because I am loath to be quoting Donald Rumsfeld. And that goes back to the horseshoe theory of politics, and there we are at the back of the talk again. Okay, fine. So, unknown unknowns. These are directed but unfocused searches. Okay? Let me give you examples. Okay? Deep peritectic, and we find solutions. Okay? You have to have names for things. What do I mean by deep peritectic? And as we get into this, understand, these are just ways of rationalizing searches. Okay? One of my favorite quotes is, "Seek and ye shall find, the unsought goes undetected." The motivation for looking is not important. The fact you're looking is important. These are just rationalizations for exploring. Okay? So deep peritectic. Here's a binary phase diagram, platinum and tin. This is a congruently melting material. On the other hand, these materials have peritectic decompositions, which means that if I heat this up, I have solid, 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 and at this point it decomposes into this solid, and this liquid is what metallurgists call a squishy solid, and only here I have a liquid. More importantly, that means if I were to try to cool down the stoichiometry, I would first grow this phase, then this phase, then this phase, then this phase, and have some tin left over. It would be a mess. Deep peritectic for me is a compound that has several other compounds on top of it and could only be grown in single crystal form, probably by solution growth. Okay? So if you look at phase diagrams and find, for example, platinum tin 4, okay, this is probably something that hasn't been looked at in single crystal form, and probably, if it has been, it's by one of my former students or someone else doing solution growth. Okay? So this is sort of an entertaining way of saying, look, these are known compounds, and probably there's not a lot known about their single-phase high-purity properties. Let's see what we can find. And as we study them, it's interviewing the compound. Do you grow? Yes. Are you interesting? If the answer is yes, we'll keep going. If the answer is no, we'll move on. No, but I mean, this is how you do basic research. You interview nature. Okay? So, let's see. Platinum tin 4. Lovely. We can grow this out of a vast excess of tin. We get beautiful single crystals using these printed alumina crucibles that we've developed. Is really important because you need sort of biggish holes to have the tin decant because it has surface tension at these temperatures. Lovely. What do we do with it? Well, this material, when we looked at it in 2012, it was before titanic and extreme magnetoresistance. We found it has an incredible triple R. And it has a phenomenal magnetoresistance. We have 500,000 magnetoresistance, 500,000% magnetoresistance at low temperatures. Any property we look at magnetic field bounces like crazy. We have quantum oscillations in anything we look at. We found it an interesting material, and one of many materials that we had looked at over the decades that were sort of semi-metallic and had anomalously large magnetoresistances, and we filed away as, why? That's weird. What's going on? And basically, with the advent and our ongoing understanding of, Weil-Dirac topological materials, I'm seeing a strong correlation between materials that have anomalously large magnetoresistances and interesting topology or fermiology. So we went back to this material. This is a rare example of where we sort of reverse engineered it and said, well, we have a huge magnetoresistance. There must be something. And my dear colleague Adam Kaminsky looked at photo emission and found something that we called DRAC node arcs, which can be abbreviated DNA, but the journals don't like it when you use that abbreviation. So, lovely. Let me give another example. Unknown unknowns. Okay? We mastered zinc as a flux. It's non-toxic, but it has a high vapor pressure. We did this when we were looking at rare transition metal 2 zinc 20 compounds. You can heat it up to about 1050. It doesn't blow up. If you heat it up to 11, it blows up in silica. Okay, fine, so we know how to handle it. And as a summer project for some undergraduates, I said, why don't we try exploring some deep peritectics in zinc? Here's scandium zinc 12. It's a tetragonal material. Maybe we'll find something interesting. Okay, let's just poke around. It probably hasn't been looked at. And with one scandium, we might see some interesting scandium physics, who knows? The very first growth we got was this, and this is not Ti26. This is not tetragonal. Okay? What we discovered, really, by accident, was the second known stable binary quasicrystal, scandium 12 zinc 88. Okay? We also, and at a certain point I almost resent having to do this, we're having to redefine binary phase diagrams. Damn it, that's someone else's job. But you know, fine. We found a new compound in the binary. We figured out where its exposed liquidus is. Okay? But in doing that, we speculated that maybe you could find quasicrystals close to, as sort of deep peritectics, to what are called crystalline approximates, things that have similar structural motifs. And with that idea, we went and looked at the rare earth cadmium series. You have rare earth cadmium 6, and we redefined the liquidus line and found a new quasicrystalline phase, another binary quasicrystal, but in this case, with moments, so we can again look at the spin glass physics in binary systems. All right. We find solutions. Another way of exploring unknowns is based on the idea that sometimes you want to have a specific element as part of the mix. Okay? Let me explain what I mean. Bismuth and antimony are old friends. These are lovely fluxes. You can do lots of neat stuff with them. You often get interesting semi-metallic physics. With the arsenides, arsenic and phosphorus were very exciting and interesting, and we needed to figure out how to work with them. But at this point, come on, bismuth, antimony, arsenic, phosphorus, finish! Nitrogen. Nitrogen would be really neat to have as part of a material. But doing solution growth with nitrogen is a stone cold bitch, because it doesn't like to go, and that's a technical term. It doesn't like to go into solution, generally. Okay? Now, in flipping through binary phase diagrams, and if you think just for entertainment this guy flips through binary phase diagrams, you're right. I consider these just fun to look at and fantasize. Ooh, oh yeah, that looks good. Okay, so here's lithium nitrogen. Now, this at first glance looks very promising, because it's telling me that if this is correct, I actually can get nitrogen into lithium and it's a happy liquid. Now there's a similar indium nitrogen binary. It's calculated, not experimental. And when you do that, you end up finding out that this is a liquid plus nitrogen gas and things blow up. So I approached this very carefully and we sort of saw what we could do. So I got lithium 3 nitrogen powder, dissolved it into lithium, and then cooled down, and we could get huge, beautiful single crystals, which means you actually can have atomic nitrogen dissolved into lithium and you can grow things out of it, which is lovely. Okay? Now, one of the first things we did then is appreciate that lithium 3 nitrogen has 2 lithium sites, and on one of them we can substitute in transition metals, and when you substitute in iron, you can have local moment physics that has anisotropy larger than any rare earth I'm aware of. Okay? Now this is a weird exception to the Jahn-Teller rule, because it's a one-dimensional environment. Okay? But it was really neat stuff, and we've continued to explore other solutions that we can make with nitrogen and try to grow nitrides out of solution. Okay? So that's sort of fun. But you can take that further. Okay? There are a lot of metal volatile eutectics that are interesting to explore. Okay? And since one of my other manifestations is trying to find new ferromagnets, even hard ferromagnets, okay? one of the places we've been looking is, for example, with phosphorus, you can look at manganese phosphorus, iron phosphorus, palladium phosphorus, cobalt phosphorus. There are often these beautiful eutectics on the transition metal side. We have walked into these very carefully, figured out how to react and how to get them into solution, and these are solutions that do not have too much vapor pressure over them. So they offer the possibility of then growing transition metal rich compounds that might be the starting point for new types of ferromagnets. Or if not ferromagnets, maybe antiferromagnets. As a matter of fact, what is a failure for a ferromagnet often is an antiferromagnet, and it might be fragile, and there we are back to our other research. That's how successful research can work. Okay? So, as you can appreciate, this overlaps into on a specific compound, on a specific ground state. And as I said, really a healthy research program has these all going in, feeding into each other. Let me end with a highly contemporary example. Okay? This is still ongoing. I don't have the end of the story, but calcium, potassium, iron 4, arsenic 4 was discovered in early 2016. Okay? This is a hybrid of the 1-2 structure. There's enough contrast between the sort of C lattice parameters between calcium iron 2 arsenic 2 and potassium iron 2 arsenic 2 that when you put them together, they actually prefer to segregate into separate potassium and calcium layers. So it forms a true quaternary. Okay? This is a true quaternary that superconducts at 35 Kelvin in the pure form. No disorder, not doped. Okay? So we really wanted this compound. Okay? So we're back to the beginning. Okay? Now, this compound is not easy. This is a quaternary. A quaternary phase diagram, just compositionally, is a tetrahedron. If you want to add temperature, yeah, but it's just not pleasant. Good luck with that. But these two fine gentlemen, Ty and William, Ty is formal, William is not formal. Exactly. By the way, if you ever get it, for those of you who know Ty, this is part of the wedding picture series, and the photographers in China was getting married. They made him do incredible things. This is one of the more civilized pictures from that. But yeah, and William's just from Arkansas. All right, so you have a quaternary, but of course we say, look, let's stick with iron arsenic. Then it becomes a pseudo-ternary, and within the pseudo-ternary, they were able to identify a region of primary solidification. Okay? With that, we were able to grow lovely single crystals. In our archive posting, there's a footnote. In the group, this is called the Trump crystal, and the statement of any resemblance to any president in terms of hairstyle or hue is purely coincidental. But we were able to get it under control. And once you have a crystal under control, you're able to do lots of nice things. So we had basic characterization. We were able to show how we did an optimization in a true quaternary. We were able to look at nesting with ARPES. We were able to do a series of papers on the pure material. Okay? Now, it superconducts at 35. It has a very reasonable triple R. We're able to see very clear signatures of the superconductivity in resistivity, susceptibility, specific heat. We can see screening. We can measure HC2. In terms of what we've been outlining, we wanted a material. We studied the basic properties of superconductivity. As we started to do this, we wanted to look what could pressure do. Okay? In calcium, we have a collapsed tet. We found a half collapsed tet phase instead. But having gone through this cycle, we then wanted to see if we could ask specific questions. For example, in this material, there's no magnetism. But we expect this superconductivity to be in proximity to some type of fragile magnetism. So indeed, we were able to start with the pure material, dope in either nickel or cobalt. These scales are a factor of 2 off from each other because we think electrons are important. And we were able to see we could induce, as we suppress superconductivity, a magnetic phase that it's in proximity to, and it's actually a new type of magnetic order for the arsenides. So, ideally, these 3 types of motivations for making a sample inspire each other, feed into each other, an adequately broad research focus is really imperative to allow this sort of symbiotic interaction. So, this type of research has been encouraged and allowed by DOE over the many decades of my research, and it is really incredibly important. And I hope DOE is able to continue funding this. In recent years, the Moore Foundation has stepped in and become a really very different source of funding for this type of basic materials research also. So, I started with conclusions. This is what I started with. Let's add a few others. We need to be both humble and ambitious as we go forward. Humble in recognizing there are many unknowns that can only be discovered by broad discovery-oriented synthetic programs. We're not at the point where we can predict everything. If someone says, oh, materials by design, we can predict everything in silica, grab your wallet and run, because snake oil is being sold. Okay? Now, on the other hand, we need to be ambitious to make these discoveries more frequent by taking advantage of any and all new experimental, computational, and theoretical advances. I think computationally, by interacting with computation, we have a chance of making this more, making these discoveries more timely, more rapidly, but there has to be an appreciation that sharp questions need to be asked and answered both experimentally and computationally. So this is, I think that discovery and experiment play a key role. We're not obsolete yet, but it behooves us to try to interact with computation and theory. But I mean, computation is what's being thrown out there a lot, as much as we can. So with that, I say thank you very much. I think I have time for questions, and there we go.